Yes, hi, I'm Lena. I'm going to present ongoing work with Ānrán, Wáng, and Benjamin Kaminski at Saarland University. And a quick disclaimer, I'm filling in for Ānrán, so credits to her for the slides and everything. But yeah, I want to start with giving you an idea of what this is going to be about, partial incorrectness logic. And well, we've all heard of total correctness logic, right? A program is totally correct if all computation started in some set of initial states, always terminates, and always does so in some set of safe states, the post condition, right? But proving termination is quite hard. So there's this more lenient notion called partial correctness, which does not require termination. But should the program terminate, it still has to do so in this set of safe final states. So we can get a proof of total correctness by proving partial correctness and termination. Okay, so then there is this, in many ways, dual notion incorrectness. And well, the claim is kind of, if it's so dual, we expect some kind of similar equation here, right? To split this total form of incorrectness into something like partial incorrectness and whatever. So this talk is going to be answering mostly two questions. First of all, what do we mean by partial incorrectness? And we'll see that this gap here can actually be filled by reachability. Okay, so I'm going to start with some formal basics. A Hoare triple is valid for total correctness, as I said before, if all computation started in this set of green states, the precondition, terminates in this post-condition C. And, well, divergence is not allowed, so this could not be a part of the precondition, but this top state here could be because it's also terminating in the postcondition. And then these three sets here actually form the largest set of states that we can fit in there. So this is the weakest condition that has to hold, and this is exactly what is captured by Dijkstra's weakest precondition transformer. And so for a given postcondition C, and a program, this weakest precondition contains all states from which computation always terminates in the postcondition. And there is another notion of these transformers called the weakest liberal precondition transformer, which additionally includes states from which computation diverges. So this state here is now also included. And why am I telling you this? Well, we can characterize both total correctness using these weakest preconditions by requiring that the precondition is included in the weakest precondition with respect to the postcondition, and we can characterize partial correctness using this weakest liberal transformer. And as I said before, we can now prove total correctness by proving partial correctness and termination. And well, this is cool because, first of all, we get something like a separation of concerns. We split the termination proof, which is like there's a whole field of research on proving termination, so this could be helpful. And also, there is this property of weakest pre and strongest post. Weakest pre and weakest liberal pre, because the weakest pre is defined as a least fixed point. So to prove this equation here, we need a lower bound on a least fixed point, which is just computationally hard to prove. For weakest liberal preconditions, they are defined as a greatest fixed point. And to prove lower bounds on greatest fixed points, we can use a very nice lemma referred to as Park's lemma or Park induction. And this makes this proof of partial correctness a bit easier. So this is another reason why it might be helpful to split total correctness into partial correctness and termination. Yes, so and now what we are going to see is that we can actually do a very similar thing for total correctness and then partial incorrectness. I said correctness, I meant incorrectness, by using these strongest post transformers. So we'll see in a second what this is exactly, but we can define total incorrectness, so this is the standard incorrectness logic using the strongest post transformer, and then partial incorrectness as some liberal variant of this transformer. Okay, so now we'll see what this is exactly. So incorrectness logic, as you all probably know, was introduced as reverse Hoare logic before, and then later reinvented as incorrectness logic. And it means that all states in some postcondition C are reachable by the precondition. And what you can see here, well, this unreachable state is not allowed in the postcondition, but this state here would be allowed. And then these two states form the largest set again that would be allowed here. And this is exactly what is computed by the strongest postcondition transformer. So for a given set of initial states, this computes the largest, all final states that are reachable from this set of initial states. Okay, so far so good. This is quite well known, I assume. And now to get from weakest pre to weakest liberal pre, I said before that we allow diverging computations. And now we want to do like a dual thing to this. So a diverging computation is like a computation path that is leading to nowhere, right? So the dual thing for a final state would be something like a computation that is coming from nowhere, so no initial state can reach this final state. So the final state is unreachable. And this duality between unreachability and divergence was also discussed in other works, for example, by Ascari and others. And yeah, so to get from strongest post to strongest liberal post, we allow unreachability. And yeah, this was exactly captured by the strongest liberal postcondition transformer, which was introduced by Wáng and Kaminski. And yeah, what this computes is the set of final states that are either unreachable or reachable by the precondition. So in other words, we say it's okay if a state is unreachable, but if it is reachable, then it must be so from the precondition. So this is very dual to this weakest liberal precondition idea. Okay, and then, as I said before, we can characterize total or standard incorrectness logic as an under-approximation of the strongest post and get partial incorrectness by under-approximating this liberal variant. And what we also get is the same computational advantage as we had for the weakest pre-case, so to speak, because we have here an under-approximation of the least fixed point, which again is hard, and here we have an under-approximation of a greatest fixed point, which is easier. And also we get this separation of concerns idea that we can split this reachability proof from the incorrectness proof. So this might be interesting to look at if we are trying to prove total incorrectness. Okay, so why should we be interested in this partial incorrectness logic? Well, total incorrectness requires reachability of all final states included in this postcondition. And this is a very strong requirement, actually. This now goes in the direction of what we've just seen, actually. I have an example that is also very similar, also inspired by one of the beginning examples in this incorrectness logic paper. Because yeah, here's a program that increases y by 1 if x is even and otherwise multiplies y by 2. And if we're now looking at this triple here, y equals 10, program y equals 11, well, is this valid for incorrectness, or are these states reachable from these states? You'd maybe think yes, because we can choose this branch here, increase y by 1, and then we end up with y equals 11. But it's actually not valid for total incorrectness, because we require that all states where y equals 11 in the end are reachable from this precondition, which is not the case if x is odd. So for example, if x is 1 in the end, it must have been so in the beginning because the program doesn't change x. But then we end up in the second branch. And well, if we start with y equals 10, then in the end y will be 20 and not 11. So what we could do to fix this is we could make the postcondition more precise. So we could say, okay, this is not valid for total incorrectness, but this here is if we specify the postcondition as y equals 11 and x is even, then we guarantee that this first branch was taken. So this would be valid for total incorrectness, but this, in some cases, it just might be hard to specify it like this concretely, right? So what we propose is to look at partial incorrectness in this case, because it turns out that these counterexample states that we've seen before, they are not just unreachable from the precondition, y equals 10, but they are unreachable from any state, at least assuming integers, because if we start with an x that is odd, then we must end up in the second branch, so y must be even in the end. So states where y equals 11 and x is odd, they are just unreachable at all. So this is valid for partial incorrectness. Okay, and I want to mention a second idea where this might be helpful, which is very similar to the motivation of necessary preconditions. Because if we're looking at this triple B pre-true, so we're including all states in the postcondition, what this says, if we have some program, all executions must have originated in this precondition B, because we require that all final states are either completely unreachable or they are reachable from this precondition. So B can be thought of as like a necessary condition that has to hold for the program to do anything or to have anything meaningful. So for example, it's a bit of a toy example, but if you think of like a Schrödinger's cat situation, you have some kind of box that you could open or not, and you have a cat inside the box, and well, the cat could be alive depending on or not, depending on whether some poison was spilled or not. This is like the program graph representing this situation. And then you look at the triple open program true, which is valid for partial incorrectness, then you know that in order to know anything about the cat in the end, the box must have been opened. So yeah, in order to make any observation, you have to open the box. Yeah, and proving this for total incorrectness is hard because you would require reachability of all final states, which is in many cases not a sensible assumption. Yeah, so to summarize, we've seen this duality between correctness and incorrectness, and we've seen that we can express total correctness as partial correctness and termination, and dually total incorrectness as partial incorrectness and reachability. And using this Park's lemma, we can prove both partial variants easier. And yeah, this can be useful when we want to relax these reachability conditions in the postcondition. And yeah, also to find preconditions that are responsible for some kind of outcome. And yeah, this is ongoing work. This is still a bit of an idea. So there's a lot of things to do. For example, the strongest liberal post-calculus that I mentioned was introduced actually as a quantitative transformer. So it'd be interesting to see what partial incorrectness means, what we can do with this in a quantitative setting. Then I've said that we can split this proof of reachability from proving incorrectness or total incorrectness. It would be cool to look at some methods how we can prove reachability, maybe using these strongest liberal post transformers. And a remark on the name partial incorrectness, because this kind of suggests that this is a bad or an unwanted property of the program, which is not necessarily the case, as it is also not the case for correctness logics that they prove necessarily good properties about programs. So this is also that I've been, the name is up for discussion, let's put it like that. Yes, thank you, that's about it.
Okay, since we got a little bit behind, we'll just take one quick question while the next speaker sets up.
So, nice talk. I really appreciate that you defined this new languages allow some Hoare triple. It doesn't allow in in-class logic, but allow in your setting. But I think in some sense, in-class logic, you can treat it as a formalization of some prosecutions. Indeed, try to prove the reachability. In some sense, in-class logic is a technique to prove the reachability, but you separate the reachability away.
That's a valid point. Yeah, sorry. I think. Yeah, in some cases it makes things harder. It's a bit. I know what you mean with this proving bugs motivation. This seems a bit silly to allow unreachability. Yes, but I think if you. Yes, this is something that we've been looking at. This is a problem. It's a valid question.
Yeah. Okay. Thank you.
Yeah.
Okay, let's thank Lena one more time.